Hi, and welcome to our note-taking guide and video segments on graphing. During this video segment and note-taking guide, we're going to look at various families, their unique graph characteristics, and the general shape of all the graphs, and start to differentiate between the families and what their graphs may look like. So what I really want you to learn here are the names of the family of functions, the general characteristics or shape of their graphs. And each family has a unique graph representation. So we're going to look at several different functions, the first being linear. They include our constant functions such as f of x equals some constant such as 2. And the functions increase or decrease at a constant rate of change. They're nice and steady. Now, linear functions usually are in the form of f of x equals mx plus b, where m is that constant rate of change or the slope of our line, and b is the y-intercept. Now, a linear function is a function whose graph, I should say, is a line. Now, if you look at the word linear, it has line right in it to help you remember that it is a line. So when we're given an equation for a linear function, we can get really important information on our variables and on that equation. We're going to look at the parent function, and that is simply the simplest form of each type of family of functions equation. So I'm going to have f of x equals x. That is the simplest form of a linear equation. Next, we're going to look at the general shape of a linear function, remembering that my parent function is f of x equals x. So I'm just going to graph that parent function to get my general shape. And if we remember, we could do x and y, or this is, remember, f of x and y are interchangeable. I'm going to get 0, 0, 1, 1, negative 1, negative 1, etc. So if I simply graph those points, 0, 0, 1, 1, negative 1, negative 1, and I could continue selecting points, but my general shape of this graph is a line that goes through the origin up to the right and down to the left. And at this point, I just want you to learn the general shapes. I'm not looking for specific points in the graphing, just the general shape of my different functions. Situations that model linear functions might be an airplane that flies at a constant altitude, height versus time, a tank that fills at a constant rate, the volume in the tank versus the time that the tank has been filling. Weekly deposits, if you get the same amount in your paycheck every week and you deposit that in the bank, the amount in your bank account versus the time you've been depositing money. Also, the slope of a roof would be another example. I'm sure you can think of another example or two of linear equations. Why don't you jot a couple of those down on the side, and we'll continue this discussion when we get together in class next time. Moving on to absolute value functions. First thing we need to do is remember what absolute value means. And what that is, it is the number's distance, if we think of a number line, from 0. So since distance is always positive or 0, absolute value functions will always produce positive or 0 outputs. So we're never going to have a negative in the range. The parent function, once again, the simplest form of this family, is f of x equals the absolute value of x, remembering that those parallel goalposts indicate absolute value. Now, the graph has reflectional symmetry, meaning if you were to put a mirror in the center, it would be the reflection on the other side. Absolute values can be defined, and it's called piecewise functions, and that means it's really, or can be described as two linear functions that intersect, but they each have a different domain or different input values. Looking at the general shape of this graph, we're going to have two lines or two linear functions, both beginning at the origin and then going up and to the right. And then when we put in a negative value, we're going to go up and to the left. So that is the general shape of an absolute value function. You would see this in the real world, real time and distance, currency exchange possibly, and in statistical use. Moving on to power functions, a power function is simply a function where the variable has a power or exponent greater than 1. So the exponent has to be greater than 1. Graphs of power functions really vary depending on the value of that exponent. Now, there are two parent functions. Don't let this confuse you. We'll see the difference because they each hold a different shape. The first is f of x equals x squared, and f of x equals x cubed. Now, all power functions with even powers, or f of x equals x squared, are going to be similar to that parent function of x squared. And all with odd powers are going to have a similar shape to f of x equals x cubed. If we graph f of x equals x squared, our graph is going to, now remember I'm not graphing the actual points, have a shape that's a parabola. And remembering that from Algebra 1, that is the general shape of all even functions. Graphing an odd function, they're all going to have a similar shape to f of x equals x cubed. Graphing this, it's going to go through the origin, 0, 0, and it's 1, 3, how about 1, 1, 2, 8, 1, 2, 3, 4, 5, 6, 7, 8, etc. And then the negatives are going to come this way. Thusly, so all odd power functions have a shape similar to this. So we'd see this in area and volume, and actually it's used when we're dealing with falling objects. So we have all x squareds, or all evens, have a parabola shape, and all odd power functions have this funny shape with the little hitch and the get along in there in the center. So that's it for this video. Please continue on to learn about a few other family of functions and their graph shapes.